Hi, Mrs. Lemke here, and I am going to be talking with you today about vocabulary related to functions. This is a three-part lesson. The first part is review of something that we believe that you already know, which is domain and range as it pertains to functions. We are going to be discussing when functions go uphill or downhill or stay the same, so increasing, decreasing, and constant. And we're going to be discussing some symmetry. So you'll notice that in my Bitmoji, I have these Valentine heart balloons, and that is because hearts are symmetric. They have the kind of symmetry where you can fold them in half and they match up with the other half. So symmetry. And that's involved in even and odd functions, okay, the idea of symmetry. All right, so to review the idea of domain and range, I know I have had students in the past get a little confused about these two ideas or sort of like mix them together somehow or something like just reverse the two. I don't know. Notice that domain and range, if I put them in alphabetical order, they are as I have them listed here. Domain pertains to what is traditionally the x variable and range to the y. So if you alphabetize x and y and you alphabetize domain and range, that can help you remember that domain is about x and range is about y. Now understand your variables don't have to be x and y. They could be t and p or something, right? So what do I mean by x? I really mean the input variable. So domain is the possible input values for a function. And range is the possible output values. And I think the reason why, I've thought about this quite a bit in my teaching career, I think the reason why this idea is sort of hard is because you're looking at a two-dimensional picture and you're trying to describe one variable or the other. So it's sort of like you have to take a two-dimensional thing and think of just one of the two dimensions instead of thinking of both of the dimensions. And that's just, it's kind of weird. So I have a strange way of explaining this, but I'm going to use it anyway. Okay, so I want you to imagine that you have something that kind of like smashes things. So like there's one, oh, Fry is going to judge me for not knowing this, but there's one of the original Star Wars movies. I want to say it's Empire Strikes Back, where maybe Return of the Jedi? I'm not sure. Where there's a scene where there's like a trash compactor and you know the three heroes are in this trash compactor and the walls like start coming in and like squishing them. Okay, so if you know the scene I'm talking about, great job, very impressive. And if you don't, I don't blame you, you're very young and this is an old movie. So in any case, what I want you to picture is like, there's like a trash compactor, like this edge is coming in and squishing that graph down. And then there's a squishing in that comes from the side. I don't know why it says, that's just what my brain went to today. And so as this smushing comes down, and as this smushing comes up, everything is being smushed onto the x-axis. So this graph, like this circle would still be there, but then like all of these points along here would all get smushed. Smushed is a very technical term that I'm saying over and over again. Would all get smushed onto this axis up to here, right? All of that. So smush, smush, smush. Okay, and then this part down here would, because of the walls coming in both directions, this would all get smushed up to here. So this open circle would lie on top of that filled in circle, and then all of this would like get brought up here. And because this has an arrow, that means that this keeps going forever, which means that when you smash it up onto the x-axis, that would keep going forever as well. Okay, so now I'm going to take out all of the things where I was just trying to point. And I want you to observe, once I get rid of all this extraneous stuff, I want you to observe where the x-axis is colored in. Okay, where's the x-axis colored in? Well, if we're counting by ones here, 1, 2, 3, 4, that's -4. So we would say that the domain started at -4 and kept going forever this direction. So if we were writing our domain in interval notation to say keeps going on forever and ever getting bigger, we use a positive infinity or regular infinity sign. And then the fact that this is an open circle means I do not include the -4, but I include everything from that point onward. Okay, so that's my domain. Now, do I need to smash all of that and all that? No. I mean, if you can just look at the graph and you saw that answer, well, good for you. You don't even need this conversation that I'm having here. Okay, let's go the other direction. Okay, so for range, I want to think about the Y values or the output values. If I do this graph smashing technique, I'm smashing onto the Y-axis now. So this piece of graph would smash over to here, right? If you're like pushing from this side and pushing from this side and you're pushing everything to be on the Y-axis. And then this part of the graph over here would be over here, and this little piece up here would be right here. And now I'm going to erase all of the extra stuff that was just me pointing or talking. And you tell me what part of the Y-axis is colored in. This time it's actually two pieces, right? So start from the small, right? So from negative infinity up until -1, not including -1. There's a gap here. That part is not colored in. And then we pick up again starting from 0, going up 1, 2, 3. Do I include the 3? I do. Do I include the 0? I do not, because the 0 has a circle. Sometimes you'll see this just like a comma in between. Sometimes you'll see it with like a little union symbol, which is what I was just trying to write right there. Okay, just means this interval along with this other interval. Okay, so that's domain and range, at least one way to think about it. You can look at an equation and think about domain and range. Like if I have a square root, I don't want to have a negative in it because that leads to complex numbers. If I have a division, so I have something like this divided by something down here, I don't want to have 0, right? You can't divide by 0. So sometimes you won't have necessarily a graph. You might just have an equation like y equals this. This is f of x, something like that. So if you have an equation, you might not have a graph to use this like smushing technique, but what you should think about is just like what can x be and what can't x be, okay? And what x can be is your domain. Okay, hopefully that helped you review. So again, these are questions that are approaching this from the standpoint of a graphical example. I do want you to try these for yourself. They are in your notes for today, so you have these pictures. And I would like you to tell me what the domain and the range are. I'd like you to write your answers using proper interval notation. So think about how in an interval you have the small thing, comma, the big thing. And then think about the open bracket and the closed bracket. You can't have a closed bracket on an infinity. Okay, we'll talk more about that in just a second, okay? But I'd like you to try these 4. And so pause the video and then come back when you're ready. Okay, good job trying those. Certainly take a minute and first just check your answers. So if you need to pause on this screen before you listen to me talk, that is of course fine. I'm not going to read through each of these, but I am going to make a few general comments. First of all, if you want to say something has a domain or a range of all real numbers, you certainly can write that in English. However, my directions out loud were to write this using interval notation. So if you have an answer that says all real numbers, please note for yourself that the interval notation for that is negative infinity, comma, positive infinity. Also, a very common incorrect answer for, let's take this one as a for example, for like range on question A, I sometimes will have students who write this, which is close, right? Like it has the same 2 elements in the interval notation, but notice that this is not correct because in interval notation, you always write the thing that is smaller and then the thing that is larger. And it's certainly, I don't know why I wrote an S on that. And then the thing that is larger. So certainly it is not the case that 1 is smaller than negative infinity, right? That doesn't really make sense. I mean, it is weird to think about infinity because infinity is a concept, not a number, but negative infinity is representing getting smaller and smaller without bound, without an edge to it. It doesn't stop. So continually getting smaller for all time. So certainly that has to be like something that represents an eternity of smallness until you get up to +1, not the other way around, so to speak. Okay, so small thing, then big thing. So your negative infinity is only going to show up on the left, in the left position, and your positive infinity is only going to show up on the right side of an interval. Now, do I want you to memorize that? No, I want you to just understand, right? That you always are doing small and then big. All right, so if any of the rest of those are confusing to you, like as you look at them, like you got them wrong, you look at the wrong answer, you look at the right answer, you try to sort it out. If you end up being confused about any of that, definitely reach out to your teacher. Okay, the next idea. So I told you this was a 3-part lesson. We're on part 2 right now. Part 2 starts with thinking about my bike. So I really like riding my bike. And I think a lot of the reason I like riding my bike is because I can think of young me. So when I was like in 2nd grade, I was really into riding my bike as well. I guess this has kind of been a lifelong thing on and off. And when I was in about 2nd and 3rd grade, I had pigtails. I wore pigtails a lot. So I had these blonde pigtails, and I also had a bike that had streamers on the handles. And I loved to ride my bike as fast as possible around my neighborhood up in Minnesota, where I grew up. And I just loved when my pigtails would fly out behind me and my streamers would fly out behind me. I thought that was just excellent. And so if you consider this, this is a picture I took of my bike along one of my rides this past summer. And this was on an actual pretty flat section of the Des Plaines River Trail. And so kind of boring in some ways, like gorgeous, right? I mean, like the scenery is amazing. If you guys haven't gone up and down the Des Plaines River Trail, oh my gosh, you really, really have to. What if you leave for college and then you never like live in this area again? You really, you know, you're missing out, I'm telling you, okay? So sometimes we ride, sometimes when I'm riding my bike, the trail is pretty flat like this. But sometimes you get to a part that is kind of hilly, okay? And so my little picture here, I know it looks like a graph as well, but if you think about this as being like a bike trail, this part of the bike trail is going to be like kind of hard. And then this part is where I'm going to channel 7 and 8-year-old me and be like, wee, and think about having my pigtails fly out, which you can't do now because bike helmets and things. But, in the 70s, we did these things. So this would be like the very fun part where you're going wee down the hill, and then you'd have to like actually kind of downshift and like work a bit, right, going uphill. So the idea of the next part of our lesson is really just as simple as these pictures, right, and thinking about riding a bike. So we read graphs from left to right, just like we read the English language. And when we look at a picture, when we look at a graph, and we're reading from left to right, we want to be able to describe if the graph is going uphill, if it's going downhill, or if it's staying the same. Those 3 ideas are encapsulated in these 3 vocabulary words: increasing, decreasing, and constant. So you can see that I associated one of those words with each of the terms that we tend to use in mathematics, okay? So the words I wrote in black are the words that I would use if I were riding my bike. Those aren't the math words. The math words are increasing, decreasing, and constant. But the bike words are uphill, downhill, and flat. Okay, we get that. So technically, we could say that if a function is increasing, that means that the y coordinates are getting bigger, right? Increasing means getting larger, right? If my weight is increasing through COVID because I'm spending too much time eating cookies that I baked, right? That means I'm gaining pounds. I'm increasing my weight. There's more of them, right? So y's are getting larger. Which means conversely, this must be when the y's are getting smaller. So what is this? Y's are staying the same. And if that flatness lasts for an interval, right, you really see a flat section of the graph, okay? So you can think of this too in terms of slope, right? Just like I was talking about with the bike ride. Over here, oops, hand hit that. Over here, think about having like little lines that sort of just were lying against that curve. All of those lines are tilting this direction. That's a positive slope. and you think of little lines over here, kind of lying against the graph, those are tilting this way. That's a negative slope. So we can think about increasing and decreasing relative to the slope of the curve as well. And if it gave you pause right there to think about a curve having slope, welcome to calculus life. Okay, that's a little bit of a glimpse, that whole idea of little lines that were lying on a graph. Calculus. Okay, so slopes are positive if we have a curve that's increasing. And you can think about these little lines, right? And if they're tilting upward. And then over here, we would say slopes are negative if we have something that's decreasing, because those little lines would be going down to the right, right? We read things from left to right. So as I move from left to right, the graph is going from higher to lower, right? You have to think two-dimensionally here too, kind of tricky. And here, if I have something that's actually flat for an interval of time, or actually for, like, I drew it for all time, what's this line slope? 0. 0 slope. Boring, right? Like this stretch of the trail, kind of boring, but also really great, you guys. I'm just saying, right? I understand that road biking has like a lot of glory to it, and people love like putting on the little biker outfit and being all fast and whatever, but nothing can compare with being out in the trees. I'm just saying. Okay. All right, so number 2, which is in your notes, is just a slightly different way of asking about this content. And so in this one, we gave you intervals and we gave you a graph, and we said, okay, use the graph, and we want you to say, like, what is it that's happening on each interval, and also tell us about the slope of the function on that interval. And we started out being a little tricky, actually, to be honest. Okay, I'll do the tricky one with you. So from -7 to 1, that's this section of graph that's in green. And if I were to think about those little like lines that lie against the function, these all seem to be tilting. Like some of them are steeper than others, but they're all tilting so that if I move from left to right, I'm going up. If I move from left to right, I'm going up, right? Going up as I move from left to right. So I know that these slopes are positive, and the idea that goes with that is that my function, the original graph, that green graph, is increasing. And the reason why I said this is tricky is because there's one spot right here, this yellow dot. I probably shouldn't use yellow. Let's see. Purple. Okay, so at that purple dot, if I were to draw one of these like little lines, that little line, to my eye, sure looks like it's going straight up and down. Does a line that goes straight up and down have positive slope? What kind of slope does it have? Rise over run? It's like I rise some amount, but I run not at all. So my rise would be like some number like 2, and my run would be 0. Is that kind of wanting me, like, do you have the heebie-jeebies right now? I hope so, because we shouldn't be divided by 0, my friends. That's a math, you can't do it, it's impossible. So 2 divided by 0 is not a defined number. So we say the slope is undefined. So there is a place within this green graph where the slope is not positive. And at that one spot, the slope is undefined. Okay, I did not leave myself space to write that. Okay, so there is one spot in that interval where the slope is undefined. And I just wanted to make that note. Now, if right now, I'm just going to call you on it. If right now your thought is panicking because you're worried that this question is going to be on your unit test, just take a deep breath, okay? We are not that mean. We are mean, but we're just not that mean, okay? So I promise you this is just an exposure situation. Calculus teachers are teaching your pre-calc class, which is a good thing, right? We're getting maybe a little ahead of ourselves, This is a key idea in the beginning of a calculus class, okay? That you'd have this undefined slope sometimes, all right? So don't get too bent out of shape about it. What I want you to take away from this particular question from part A is be like the main, every place along that whole green section of curve was increasing. There is one spot that we would have to worry about in our calculus class because of that undefined slope, okay? B, C, and D, we can handle this. B is this section here. Is that increasing, decreasing, or staying the same? Okay, write down your answer. The next one is this section. Increasing, decreasing, or staying the same? Okay, write down your answer. And the last one is this section. Increasing, decreasing, or staying the same? Write down your answer. Okay, let's check our answers. Okay, here's my neat work. See, when I'm not under time pressure, I do have a reasonably good handwriting. Not great, not Fry's handwriting. No one has that, okay? That's a gift. Okay, so you should have said decreasing, increasing, and decreasing. And notice that with B and C, I did give you a couple of more, like just an extra note. Again, the calculus teacher in me just can't pass this by. This section of the graph is linear. And in fact, I could find the slope of this line. I can see, or maybe I can't. I don't know that that's exactly on 5. But if I could, if I had more actual data, then I would be able to find the rise and the run and be able to say, oh, the slope of this section of graph is negative whatever that number is. But it is a certain number because lines have constant slope, a fixed slope. So that's what I was noting there. It's a fixed negative number. Just like in this section, I'd have a fixed positive number for my slope. Through this part, the slopes would be changing, right? Because this part isn't a line, it's a curve. And when you have a curve, the slopes change. They don't change in sign, though, in this section. All of the slopes would be negative because the graph is going downhill. It's just that the slope isn't a certain number throughout. Okay, so in this part, what I'd like you to do is to pause the video and try. So in this one, you're given the graph, and we want you to come up with the interval or intervals for each of these things. Where is the graph increasing? In other words, where are you biking uphill? Where are you going way down the hill, noticing your streamers from your bike handles? And where are you staying the same? Okay, so pause the video, come back in a couple. Okay, so here we are. And you can see in my picture, I color-coded the parts that are uphill as red because it's like harder to bike up. It's more like a red light. And I coded the parts that were downhill green because that's like the wee, you're going really fast. It's like go, okay? So increasing and decreasing intervals are listed there. If you don't have the union symbol, you could just have like a comma or nothing. That's fine. And then notice the constant. There weren't any sections of this graph that were flat left to right, like a section, right? It wasn't like I had like an uphill and then like a flat like that, right? So there weren't any places like that. However, there are, and again, previewing calculus, just shh, it's okay. So there are places where you have like a hill or a valley. And technically speaking, this is what we would call having an instantaneous moment where you're not increasing, you're not decreasing. So if you're not doing either of those, what do you have to be doing? You're staying constant for just a split, like not even a split second, instantaneously, okay? So what I would say is here and here and here and here, we have some interesting points to talk about, okay? And so that black color coding goes with this black writing. The two that are up here at the tops of the hills, we would call those relative maximums. And these 2 points at the bottom are relative, guess, right, minimums. A maximum is something that is as big as possible, like the maximum points possible on something, right? You might say, oh, the maximum possible on this quiz is 100 points, right? That's the most. So you might say, well, why do we have two different points that are both called relative maximums? I mean, certainly the one here on the left is higher than this one on the right. Well, that's the word relative. Okay, the word relative just means within its neighborhood, within the points right around it, like within a little area, it is the highest such point, right? And that would be true over here too, right? Within this little neighborhood, it's the highest such point. Okay, so you can kind of loosely think of it like a hill. It also can be like the point of a mountain though. So be cautious about the word hill, like it might look spiky like that. And this would still be a relative max. Another term for relative max, sometimes you'll see them referred to as a local maximum. And I kind of like that because local means like, okay, so say like within Lake Forest High School, you have the highest ACT score. That's the local high, the local max. But within the whole country or in the whole world, you have the highest ACT score. That would be like what we call a global maximum or an absolute maximum. Means that you're the highest of the high, right? And a local max or a relative max means that you're a high point within a smaller section. Hope that makes sense. Okay. And then the relative min, it's the same idea, but just low points. Okay. These terms are just previewing some calculus terms. Okay. It's just good for you to see. I mean, how fun is that? Learning calculus today in a pre-calc class. Yay. Okay. Third part of the three-part lesson. Some terms that involve symmetry. Now notice that when you think about natural numbers, numbers like 12 or 39 or 17, right? Those numbers, you would either say they're even or odd, right? This one is even, okay? Is this one even? It's not even. Oh, so that means it's odd, right? And this one's odd as well. So numbers like that are either even or odd. With symmetry, we use those same words. However, it's not an either or situation. You can have a picture, you have a function, have a graph, and it might be even, it might be odd, but it might be neither of those. Okay, so just bear that in mind. Something I don't like about this particular choice of vocab. Okay, so a function that is even has y-axis symmetry. So I mentioned ages ago at the start of this video how the Valentine hearts in my balloon picture back there were symmetric, right? So y-axis symmetry is when the y-axis is like the red line in this picture. You fold the graph, it matches up with itself. Odd symmetry is rotational symmetry. Okay, and this is reflection symmetry, I should have said. I'm going to fix my wording here. Reflection symmetry across the y-axis. That's better. Sorry about that. Sorry about the scratch out. Everyone who wrote with pen just cursed me out. I'm sorry, guys. Okay. So reflection symmetry across the y-axis is an even function. Rotational symmetry around the origin makes something an odd function. So something that maybe looks like this would be an odd function. You imagine putting your finger right here and the axes are glued in place, but the graph itself, like this part of the graph, if you spun it around, it would fit here. And if you spun the green part of the graph around, it would fit on the red part, right? That's rotational symmetry, okay? So if we just take a glance through these, A, is it even, odd, or neither? This one's even because there's this line of symmetry right here. How about this next one? Well, I see that there's symmetry. There's a line of symmetry here, but that's not on the y-axis. So we're going to say neither. There is symmetry. It's not the special kind that's even, and it's not the special kind that's odd. How about this guy? Well, if you imagine gluing down 0, 0, and then spinning this graph like that, right? So imagine that the graph can move, the axes stay in place. Does one piece match up with the other piece? Does one chunk match up with where the other chunk is? Does the black fit onto the green, and does the green fit onto the black by spinning? The answer to that is yes. That's an odd function. Okay, so when you do a visual test, that's how you determine even, odd, or neither. But sometimes we need to do an algebraic test. The algebraic test is to replace x with negative x, or the opposite of x. And if f of negative x gives you your original function back, then you have an even function. This should make sense. If you look over here, you can see, like, if I did f of 1 versus f of negative 1, f of 1 is maybe here, f of negative 1 is here, and you can see I get the same thing, right? This is the same y value. So f of 1 equals f of negative 1 is a special case of this statement in blue. Odd functions, if you insert the opposite of x into x, and if every single sign changes, oh, sorry, my dog just barked. I'm sorry about that, you guys. There's someone outside, like there's another dog on our street right now. She's going to lose her mind. So if you replace x with negative x and you get all of the pluses and minuses to switch, every one of them, then you have an odd function. Okay, so let's try an example of that together. So in this problem, if I were to do the algebraic test, and I would recommend doing this, first of all, if the directions say to do it, but secondly, if I don't have a graph. Right, if I have a graph, I can just look for the symmetry. But making a graph is sometimes a hassle. Okay, so I'm inserting negative x in place of every x, in the same way that if I asked you to find f of 5, you'd put a 5 in place of every x. Here, since I'm asking you to find f of negative x, you put negative x, or the opposite of x, in place of every regular x. Okay, so that's my writing in green there, is replacing, and so I can find f of negative x. Right, in my next line of work here, I will just do some algebraic simplification. So opposite of x times another opposite of x is going to be positive x squared. Okay, let's look at this result. Notice that it is the same as f of x. So if you look at what I started with here and what I ended up with and how it's linked with an equal sign, I have the exact statement up here of being even. So this function is even. I would like you to try the other three and then check your work, okay? So please pause. Oh, heck, I thought I had that on pause. I apologize. Okay, so here you insert negative x and you end up with something that is sort of the same but sort of different. So it's not like all of the pluses and minuses match. It also is not like they are reversed. So in this particular case, we would say neither. And the last two, hopefully you paused and didn't just sit there with me. Sorry about that. So with these last two, if you insert the opposite of x for the function h, you get an odd result. And for the last one, you get an even result. This one is a little tricky because you do have to think about how. I'll take an example. If I have the cube root of negative 8, that's negative 2. And if I have, so if I have something like this, and it is to the 4th, I'm going to get a positive result. And so this part here is the same as having the cube root of x raised to the 4th. Just like if I had the cube root of positive 8 raised to the 4th, that would be just like 2 to the 4th. And these give the same result. So that part is a little bit tricky, okay? Great job on this. In our next class, we will do practice on all of these ideas, and we will add on one more component, which is inverse functions. Thank you.